There is a man in rural Montana who has not paid a heating bill in 3 winters. Not because he installed solar panels, not because he found a government subsidy loophole, not because he lives in a cabin too small to matter. He lives in a regular house. He has a family. And every winter when the temperature falls below zero and his neighbors are staring at $400 utility bills, he builds something on his kitchen counter with 2 items he already owns and 1 ingredient that costs less than a cup of coffee. And his house stays warm. What he figured out, almost by accident, is a chemical reaction sitting in industrial textbooks since before the First World War. A reaction requiring no electricity, no gas line, no combustion, no permit, and no ongoing cost. A reaction so effective that the heating industry spent the better half of a century making sure it never became common household knowledge. Welcome to QuickSecret. If you found this channel, you are the kind of person who asks questions that most people stopped asking. Good. Because today we are pulling a thread that goes all the way back to 1912, runs through military field operations, Japanese convenience stores, industrial chemistry labs, and the boardrooms of companies making billions every year off the assumption that you do not know what you are about to learn. By the end of this video, you will understand how to build a heat source for under 50 cents that holds above 120 degrees Fahrenheit for up to 12 hours, why you were never taught this in school, and what it costs you every year just to stay warm inside your own home. This is not a life hack. This is a buried chapter of applied science, shelved the moment centralized heating became profitable. Let us go back to where this story starts. The year is 1912. The world smells like coal smoke and machine oil. The Industrial Revolution is a generation old, and chemistry is in its golden era. Laboratories across Europe and North America are cataloging reactions and building the foundational vocabulary of applied science that engineers would rely on for the next century. And in those labs, something keeps showing up. When you expose finely divided iron, iron broken into small filaments with a large surface area, to water and oxygen, it oxidizes. Everyone knows this. Everyone calls it rust. But what the chemists of that era were documenting with precision is something casual observers miss entirely. The rusting of iron is not just a chemical change, it is an exothermic reaction. Exothermic means it releases energy, not light, not sound, heat, real, measurable, sustained heat that radiates from the iron as it oxidizes and can be captured, concentrated, and used. The amount of heat is not trivial. Oxidizing 1 mole of iron to iron oxide releases approximately 826 kilojoules of energy. Peer-reviewed, present in every serious electrochemistry reference ever published. Not an estimate, a thermodynamic constant. The problem in 1912 was the same one you observe on a rusty fence post. Under normal conditions, the reaction moves so slowly that the heat it generates bleeds into the surrounding air faster than it can accumulate. You never feel it because it never builds. But those chemists asked a different question. What if you could speed the reaction up? Strip iron of the thing that slows it down, expose fresh reactive surface to oxygen, and do it fast enough that heat output outpaces heat loss? The answer was already sitting on every kitchen table in the world. Salt. Not salt as a flavoring. Salt as an electrochemical weapon. When sodium chloride dissolves in water, it releases chloride ions. Chloride ions do something very specific to iron. Under normal conditions, iron develops a thin passive oxide layer on its surface, a microscopic suit of armor that slows further oxidation almost to a stop by cutting off fresh iron from direct contact with oxygen. Chloride ions attack that layer at the molecular level through a process called pitting corrosion. They do not work around the armor. They chemically dismantle it, boring through and exposing bare reactive iron directly to oxygen and water. The moment that happens, the oxidation rate accelerates dramatically. Rust that would normally take weeks is compressed into hours. Heat that would normally bleed away unnoticed is now generated fast enough to feel, fast enough to measure, fast enough to use. This is not folklore. This is the same mechanism behind why road salt destroys car frames. Why iron structures in salt water corrode at 4 to 5 times the rate of identical structures in fresh water. It is demonstrated in every corrosion engineering course at every serious university on Earth. In 1912, the chemists documenting this knew exactly what they had. A cheap, portable heat source with no moving parts, no combustion, no fuel line, and no infrastructure requirement. Just iron, salt, water, and air. So why had you never heard of it before you clicked on this video? Because of what happened between 1940 and 1960. Before the Second World War, heating in most of the developed world was decentralized. People burned wood, coal, kerosene, fuel sources bought by the load from a local merchant. No company owned your winter. No pipeline ran into your basement. No metered system charged you for every BTU your family consumed. That changed with the post-war boom. The build-out of centralized natural gas infrastructure across the United States and Europe was one of the largest industrial projects of the 20th century. Pipes under streets, distribution networks, processing plants, furnace manufacturers, thermostat companies, billing systems. By 1960, warmth had been transformed from something you produced into something you purchased. And that transformation was worth a fortune. Today, the global heating equipment market, just the equipment, not the fuel, is worth over $128 billion annually. The average American household spends more than $900 every single year on heating fuel alone. Multiply that by 130 million households, and you have a revenue stream so enormous that the industries living off it have every incentive to ensure that a 50-cent alternative never becomes general knowledge. They did not need to suppress the chemistry. They did not need to burn the textbooks. They just needed to make sure nobody was talking about it in plain language to ordinary people. And for 80 years, through the simple force of cultural inertia, they succeeded. Here is what that silence looks like in practice. By 1988, Japan was manufacturing 450 million disposable iron oxidation hand warmers every single year, not as a survival novelty, as a mainstream consumer product in every convenience store, every pharmacy, every train station kiosk. The chemistry was not hidden in Japan. It was sitting on a shelf between chewing gum and lip balm. In the United States at the same time, the identical chemistry was available only as a sealed single-use product sold through outdoor retailers at $3 to $4 per unit. The ingredients inside each pouch cost a fraction of 1 cent to produce. The markup exists entirely to prevent you from understanding what you're buying. You buy the pouch, you throw it away, you buy another one. You are never shown the ingredient list in plain language. You're never told the ratio. You're never invited to make it yourself. Because the moment you understand what is in that pouch, the multi-$100 million hand warmer industry becomes something you can replicate on your kitchen counter for pennies. This is exactly the kind of buried knowledge we surface here on QuickSecret. Not conspiracy, not theory, just the economic logic of suppression. The formula was too simple to patent. The chemistry was too well documented to erase. So instead, they buried the conversation. Until now. Now the third element, the one that transforms a simple pocket warmer into something far more powerful. Aluminum foil. Foil has one of the lowest emissivity ratings of any material at a grocery store. Emissivity measures how efficiently a surface radiates heat away. Dark asphalt bleeds thermal energy outward almost completely. Polished aluminum reflects roughly 97% of the infrared radiation that hits it back inward. That means heat generated inside an aluminum foil wrap cannot escape efficiently. The foil acts as a thermal mirror, bouncing heat back toward your body, toward whatever surface the pack rests against, toward the space you are trying to warm. Same physics behind emergency space blankets. Same reason a baked potato wrapped in foil stays hot on a counter for over an hour, while an unwrapped one cools in 10 minutes. When you combine iron oxidation with aluminum foil, you are not building a warmer. You are building a directional heat retention system. The chemistry generates heat. The foil concentrates it. Small gaps at the seams allow just enough oxygen to reach the iron and keep the reaction alive. Heat that would otherwise bleed into the air in minutes is held against you for hours. A complete heat source for under $1 that outperforms a $30 box of commercial warmers. Here is the exact build, step by step, nothing left out. Go to any grocery store or hardware store and find fine steel wool. Look for grades labeled 00 or 0, typically in the paint or cleaning aisle. The finer the grade, the greater the total surface area per gram of material. More surface area means more iron exposed to oxygen at once. More exposure means faster reaction, and faster reaction means more heat. One standard package runs about $2 and contains enough material for 10 to 15 heat packs. In a bowl of warm water, dissolve 2 full tablespoons of ordinary table salt. Stir until completely clear. You want a strong brine. The higher the chloride concentration, the more aggressively the passive oxide layer on the steel wool breaks down, and the faster the heat. Generating reaction begins the moment the wool hits open air. Pull a section of steel wool roughly the size of a tennis ball. Submerge it completely in the brine and let it soak for a full 60 seconds. This step is not optional. Chloride ions are penetrating and dismantling the passive protective layer on every exposed iron surface, preparing every filament for rapid oxidation the moment it contacts oxygen. After 60 seconds, remove and squeeze the steel wool firmly. You want it damp, not dripping. Saturated wool has standing water that physically displaces oxygen at the iron surface and chokes the reaction. Bone-dry wool loses the electrolyte that drives electron transfer. The target is a wrung-out sponge, moist throughout but releasing no water under pressure. Shake the damp wool gently in open air for 10 to 15 seconds. Within 20 to 30 seconds, you will feel it warming in your hand. That is iron oxidation beginning in real time. That is heat being released by chemistry. Now wrap the warming steel wool in 2 layers of kitchen aluminum foil. Fold and crimp the edges firmly, but leave small gaps at the seams, tight enough to reflect heat inward while allowing a slow trickle of fresh oxygen to reach the iron inside. Place the wrapped pack inside an insulating sleeve, a thick sock, a cloth bag, a folded bandana. The fabric protects your skin from direct contact with the foil surface, which can reach burn level temperatures at peak output, and it adds thermal mass that slows heat loss from the exterior. Within 5 to 10 minutes of completing the build, the pack surface will hold between 120 and 145 degrees Fahrenheit. That temperature sustains for 6 to 12 hours depending on volume, moisture level, and oxygen access through the seams. For body warming, one pack against the torso holds all day. For emergency space warming, the math changes entirely. A closed 60 square foot space, a small tent, a single room with drafts blocked, responds to cluster heating in a way an open room does not. 5 packs of this size, placed on elevated surfaces so warm air rises and circulates, can raise the ambient temperature by 10 to 15 degrees Fahrenheit above the outdoor temperature and hold it there through an 8 to 10 hour night. In a winter blackout at 20 degrees outside, your sealed room stays between 30 and 35. Not comfortable, but survivable. The difference between hypothermia risk and a cold night that ends in the morning. Total material cost for 5 packs, under $4. Compare that to a box of 40 commercial disposable warmers at $35 to $50. A portable propane heater at $35 to $50 per overnight session. A February gas utility bill averaging $150 to $300 for 1 month. Against all of that, $11 total, enough for a family of 4 to ride out a week-long winter blackout. Materials that fit in a shoebox. That is the math the heating industry built its entire model around you never doing. 2 limitations to understand. This method heats people, not buildings. It is a personal and small space solution that keeps a human body warm when the infrastructure that usually does that job has failed. It cannot replace a central furnace. The reaction consumes oxygen. In a tightly sealed space, run multiple large packs without any ventilation, and oxygen concentration drops. A cracked window or a gap under a door prevents this entirely. At peak output, the foil surface can cause contact burns. Always handle through fabric. Treat a fresh pack the way you treat a mug just out of a microwave, never directly against bare skin. These are not reasons not to use this method. They are the parameters of using it correctly. There's a woman named Greta who lives in northern Minnesota. 2 winters ago, a late January ice storm knocked out power across her county for 4 days. Her furnace is electric. Her backup was a gas fireplace she had not used in 2 years and could not get lit. Her husband was working overnight shifts. She was home alone with 2 children, ages 7 and 9. The temperature outside fell to minus 11. Inside, the house dropped to 52 degrees by the second night. She had seen a video months earlier about iron oxidation heating. She had not prepared. But she remembered the list. Steel wool, salt, aluminum foil. She drove 6 miles to the only open store and bought all 3. She built 7 packs on her kitchen table. 5 went into the living room, where she had moved the children with sleeping bags and blankets. 1 went into each bedroom to keep the pipes from freezing. For 48 hours, the living room held between 58 and 64 degrees while the rest of the house fell into the 40s. Her children did not shiver. They complained about watching movies on a small phone screen and eating canned soup. Normal complaints, not dangerous ones. When she told her neighbor afterward, the neighbor said it was too simple to work in real-world terms. Greta asked her neighbor where she had spent those 4 nights. The neighbor had driven to a hotel 30 miles away. $175 per night. Simple knowledge, freely acted on, was worth more in 4 days than any prepackaged emergency kit the preparedness industry had ever tried to sell her. Here is the thing nobody in the heating industry wants you sitting with. You cannot patent the oxidation of iron. You cannot own exothermic chemistry. These are laws of physics operating before humans named them, before any company decided they were inconvenient. The reaction does not care what natural gas costs this quarter. It does not check whether your utility bill is paid before it releases heat. What you're holding in that foil pack is energy that belongs to physics, not to an energy company, not to a brand charging a 3,000% markup on sealed pouches of iron filings. To physics. And physics has no subscription fee. The reason this was not in your middle school science class is not complexity. A 12-year-old can follow these steps. The reason is economics. A population that generates its own heat for 50 cents does not need the architecture built around them. This was common knowledge in 1912, steadily deprioritized through every decade since as the centralized heating industry grew larger and more dependent on collective ignorance. Your grandparents held it the way we hold knowledge about oil changes, not as a survival skill. As basic household competence, it was not lost, it was replaced by the belief that warmth is a service you purchase rather than a reaction you initiate. Here on QuickSecret, we pull that replacement apart and hand you the original. The next time you hear a winter storm is approaching and the grid is fragile, you will know something that 99% of the people in your area do not. Warmth does not come from a furnace or a gas line or a fuel canister. It comes from iron meeting oxygen in salt water. It comes from a reaction documented in 1912 that has never once stopped working in the 113 years since it was first written down. It comes from a roll of foil, a box of steel wool, and a tablespoon of salt. It was always dependent on chemistry, and chemistry has been free since the beginning of time. If this opens something for you today, share this video with one person. Not because of the algorithm, because that one person might be the parent sitting in a cold house this February, wondering why nobody ever told them this. The industry does not ban this knowledge. It starves it of sunlight until a generation grows up, assuming it never existed. Every share is sunlight. Subscribe to QuickSecret so you are here when the next video drops. Because the next one covers something every household throws away every single week without understanding what it actually is. A substance so chemically active, it can be repurposed into a cold temperature pipe insulator, a wood preserver, and a low-cost water purification ingredient. Something sitting in your cabinet right now, something you have been discarding for years. The buried chapter opens again soon. Be here when it does.